Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Today we're going to talk about scientific notation. And scientific notation uses exponents, which is why we're putting it in our exponent unit. But you'll notice it's a little bit different than the types of problems we've been doing before. This also may be a review for some of you, depending on whether you looked at it in a pre-algebra course or in some middle school course, but we're going to review nonetheless. A couple questions to think about to get us started. How many individual grains of sand do you think there are on Earth? Write out that number below. And number two, what do you think is the diameter or the width of an atom? Think back to science to think about what an atom is. And you're also going to write out that number below. All right, so I'm sure there were a lot of guesses. I'm just going to write the number out here. And this is also an estimate. No one knows the exact amount of grains of sand we have here on Earth. But this number, and bear with me, right here is the estimate for the amount of grains of sand on Earth. Really big number. Don't even know how to say that number, right? You'd have to look it up and think about, okay, we have hundreds, we have thousands, we have millions, we have billions, we have trillions, we have quadrillions, and we have quintillion. So we have 7.5 quintillion individual grains of sand on Earth. Anyway, that's not really important. We're not testing you on knowing the names of really large numbers. Today, though, we're going to look at a way to write this a bit neater. Instead of having to write out, in this case I had to write out 17 zeros, there's a way to write this out that makes a little bit more sense. And that would be 7.5 times 10 to the power of 18. Now, which one would you have to rather write out every single time? Right, this long number or this short one that I boxed in red? Not only will today help us with numbers that are rather large, they will help us with numbers that are really small. So again, not super important whether you know the diameter of an atom. Turns out that the diameters can change depending on what atoms you have, right? A hydrogen atom may have a different diameter than an oxygen atom. That being said, this is the number that I looked up for the diameter of a hydrogen atom. We have 0.0000000000106 meters. And let's just make sure we know that these are all zeros. That one looked like a 6. But again, another number that you really don't want to have to write out every time that you want to use it. So it turns out that this is equal to 1.06 times 10 to the power of negative 10. Nice and concise. So today we're going to talk about what these two numbers are, how to write them, how to convert how to convert something like this number to this, and vice versa. And this is called scientific notation. Okay, let's look at a definition, then we'll jump into some examples. This is what we just talked about. There are times when we'd prefer not to have to keep writing out a very large or a very small number. When we come across these numbers, we can write them using something called scientific notation. So scientific notation. This is a number, or a number in scientific notation is a number greater than or equal to 1, but less than 10, and multiplied to a power of 10. So let's look at some examples here. Notice that all of these numbers are greater than or equal to 1, but less than 10, and they're all being multiplied to a power of 10. We have 10 to the 6, 10 to the power of 18, 10 to the power of negative 4. So those two things have to be true for a number to be in scientific notation. If I have something like 3.5 times 9 to the power of 8, not in scientific notation, because that is not being multiplied by a power of 10. It's being multiplied by a power of 9. If I have a number that's not between 1 and 10, so if I have, 20 times 10 to the second, that is not in scientific notation, because 20 is not between 1 and 10. I hope I said 1 and 10 before. Not 0 and 10. It's got to be between 1 and 10. So let's first just look at identifying which numbers are in scientific notation and which ones are not. Let's see if I can put all of them. Okay. So take a second, see if you can fill out or say yes or no in terms of which of these numbers are in scientific notation, which ones are not in scientific notation. Okay, so for the one on the top left, this would be no, because 22.45 is not between 1 and 10. For the second one, same reason, no, because 0.297 is not between 1 and 10. Again, that first number has to be greater than or equal to 1, but less than 10. For this bottom left, no, because 2 to the 8 is not a power of 10. And finally, this one, yes. 1.55 is between 1 and 10, and it's being multiplied to a power of 10, 10 to the power of 99. Okay, now let's look at how to convert between numbers and the equivalent form in scientific notation. So the first thing we're going to do is we have some multiple choice questions, and we want to write out the number. So we're given a number in scientific notation, and we want to write it out in long form. So we'll look at two examples. We'll look at one where our power of 10 is 10 to a negative power, and then we'll look at where 10 is to a positive power. So let's actually first look at, let's do number 4, because I think it's easier when there's a positive exponent on the 10 rather than a negative. So 4.75 times 10 to the power of 5. Well, first off, we want to think about if I multiply 4.75 by 10 to the power of 5, should I get a number bigger than 4.75 or a number smaller than 4.75? Well, the answer is it's bigger. So we want to end up with a number that's larger than just 4.75. Because it's to the power of 10, and our number system that we work with is base 10, this allows us to just move the decimal to the left or to the right a certain number of times. Again, this would not work if it was, 8 to the power of 5. But because our number system is base 10, and essentially what that means is that for each placeholder that we have, right, if I have 928. For each of these placeholders, there are 10 possible digits that can go there, right? 0 to 9. That's essentially what base 10 means. We're not going to get too much into base 10, but that's essentially what it means. If you had like base 8, that would mean that there are only 8 possible numbers that could go in each placeholder. But that is certainly a topic for a different class. Different course. So what we're going to do is this 10 to the power of 5 means that I need to move the decimal place, move decimal 5 places to the right. That is going to make my number larger. If I moved it to the left, it would make it smaller. So 1, 2, 3, 4, 5. Well, what happens when we don't have numbers there? Well, before we move this decimal, we're actually going to put some placeholders, and those are just going to be zeros, right? It doesn't matter how many zeros I put here, right? It's not going to change the number. That number is still 4.75. It just makes it easier for me to now move the decimal to understand what my new number is going to be. So I'm going to move it 5 places. 1, 2, 3, 4, 5. So my new number becomes this: 475,000. You can put the other zeros there if you want. Remember, it doesn't matter how many zeros you add after the decimal place, it's going to be the same number. Technically, though, once we move that decimal and write out our new number, we'd actually get rid of all these numbers just to clean it up a little bit, right? Because if we're going to write 475,000, we don't need to put the decimal place there. Okay, let's actually now jump up to number 1. So let's work with one where we have a negative exponent on the 10. Well, same idea, right? We're just going to move the decimal place, but in this case, we need to move the decimal place to the left, right? If I move the decimal place to the right, it's going to give me a larger number, but I need a smaller number here if I'm multiplying by 10 to the power of negative 4. And if you're wondering, well, why is this number going to be smaller? Well, let's think about negative exponent rules. 3.8 times 10 to the power of 4, negative 4 rather. Well, but by negative exponent rules, the 3.8 is going to stay in my numerator, but the 10 is going to move to my denominator because its exponent's negative. So I move it to my denominator, make it negative. Well, now I'm dividing 3.8 by a large number, right? So that 3.8 is going to become smaller. So that's why when you're multiplying by multiplying by base 10 with a negative exponent, your number is going to be smaller than that number out in front. So all I need to do is add some zeros to the left-hand side to make this moving of the decimal place a bit easier. It doesn't matter how many you add, you just want to make sure you have enough. And now I'm going to move it 4 places. 1, 2, 3, 4. So our new decimal place is there. So if I rewrite this number, I get 0.00038. And that is my new number. And I guess these are multiple choice. So we could start circling the correct answers or boxing. So A for number 1. If we look up here, we also get A for number 4. A couple of A's. You can try numbers 2 and 3 on your own. We're not going to go through them in the video, but they are the same. They follow the same process that we just did. Let's now take a look at some non-multiple choice ones. These are actually, again, the same idea. We're converting a scientific notation number to a number in its long form. You just don't have multiple choice answers here. Let's go the other way, though. Let's talk about going from a number in long form to a number in scientific notation. I'm actually not going to do the multiple choice answers here. I'll leave those for you for this, and we will work through some non-multiple choice. Sometimes with the multiple choice, you can narrow the correct answer down without actually knowing how to do it. I'm just looking at number 9, and turns out that of all 4 of these answers, only one of them is actually in scientific notation, right? So even if you didn't know how to convert to scientific notation, you could still get the right answer because, again, only one of those is in scientific notation based on the definition. I'm not going to tell you which one, but I think you could figure it out by looking at our definition up above. But let's go ahead and look at We'll do 13 and 14. So for 13, right, for scientific notation, we need that number out in front to be between 1 and 10. So I know that my decimal place is going to have to go between the 1 and the 7, 1.7. If I put it before the 1, if I do 0.17 times 10 to the something, well, that's not going to work because 0.17 is not greater or equal to 1. I can't put it in front of the 7 or behind the 7, whichever way you want to think about it, because 17 is greater than 10. So that's not going to work. So it's got to go right in between the 1 and the 7. So 1.7 is going to be our number out front. Now I need to figure out what the exponent is on the 10. Is that going to be positive or negative? Well, a couple ways to think about this, but we know that our number, 1.7, that's smaller than 170,000. So we're going to have to multiply by a positive exponent here. The other way to think about it is, if I put my decimal, let me just write this out a little larger. It'll make it easier for us. So if I put my decimal here, well, originally it's here, right? The decimal is really here. We just don't write it because there's no need to. But that's where the decimal would go, right? And I could put as many zeros as I wanted here without changing. So you got to think, how many places did we move the decimal to the left? 1, 2, 3, 4, 5. Well, we moved it 5 places to the left, which means this right here is going to be 10 to the power of 5. Which makes sense, right? Because now if I was to evaluate this, I'd have 1.7, I'd have a bunch of zeros. I know that my exponent's positive, so I'm moving to the right. So 1, 2, 3, 4, 5. And then look, there's 170,000. But again, instead of just memorizing left or right, I would try to think about it intuitively, right? If I'm starting with 170,000 and I make the number if I make the number in front of the power of 10, 1.7, well, the only way to get 1.7 to 170,000 is to multiply by a positive exponent, right? 10 to a positive power of 5. If I did 10 to a negative power of 5, right? If I did 1.7 times 10 to the power of negative 5, well, that's just like 1.7 divided by 10 to the power of 5, which is going to give me an even smaller number. So again, intuitively, we know that our exponent has to be positive, and then we can kind of count from where we started, right? Just like we did up here to where we put it, and there were 5 places that it jumped. So that's why it's 5. All right, let's do 14. Here, we know that our exponent must go between the 9 and the 2 to get 9.28, because that's a number between 1 and 10. Now, let me rewrite this for us. We have 0.000928. So here's our original decimal place. Here's the ending one. How many places did I jump? 1, 2, 3, 4. So it's either going to be 10 to the 4th or 10 to the power of negative 4. Well, our original number is quite small, right? This number out here is large. And I need to think about, okay, this number, this 9.28, I've got to think about how would I get that to equal the original number, 0.00928. Well, I'd have to make it smaller, which means I need to multiply by a power that is negative, right? So 10 to the power of negative 4. If I multiplied by 10 to the power of positive 4, I would be making 9.28 much larger. But I don't. I need it to become much smaller because that's what the original number was. So this would be our answer to 14. Would encourage you to work through the rest of these. Just to get some practice going either way, going from the original number to scientific notation or going from scientific notation to the original number. But I will leave you here for today. As always, enjoy the rest of your day. We will look forward to seeing you next time.